For RCR TV, I'm Sean Kinney, and welcome to HetNet Happenings, where we take a look at all things DAS, small cell, Wi-Fi, and much more. Welcome back to HetNet Happenings. We've got a Qualcomm themed show for you this week. Earlier in the month, I took a quick trip out to Qualcomm's headquarters in La Jolla, just up the road from San Diego. Got to take a look at some of their emerging technologies. I think the folks in the audience who are headed to Barcelona for Mobile World Congress can see these demos in person at the Qualcomm booth. But for those of you who are not making a trip, I'm glad I get to share these clips because this is some really high-tech stuff. Now, Qualcomm cuts a pretty wide swath through the wireless and mobile industries. They supply chips to Samsung for their devices as well as lots of other companies. Chances are your handset has some Qualcomm technology in it. They also play in Wi-Fi, which is what we're going to take a look at first. In this clip, we're going to see what Qualcomm is doing around the 802.11ad Wi-Fi standard adopted by the IEEE. What this does is it expands Wi-Fi from the 2.4 and 5 gigahertz bands up into the 60 gigahertz band. This has a lot of implications for consumers, particularly around next generation video. So think like 4K streaming and that sort of thing. So let's hear from Qualcomm on 802.11ad.
60 gigahertz we've been working on since about 2007, 2008. I think you saw at CES. And I know a number of you wrote about the demos that we had there and the announcements. Basically, we're taking 60 gigahertz and just bringing it to be the third band of Wi-Fi. So everything you can do in 2.4 and 5, you'll be doing in 60. And obviously, there are some unique characteristics that provide tremendous value in 60 gigahertz, right? So you're going to go up to 4.6 gigabits per second rather than the couple hundred megabits per second that you're getting in the 2.4 and 5 band. Extremely low latency, allowing for basically lag-free video. And when we were at CES, we announced pretty much all the categories that we're going to be shipping in. The access points, we saw TP-Link, NEC, Elecom, the PC, Acer and Asus, and the first LETV phone here. So before we do this demo, there's also the announcement that we made with Intel. So now, again, all of the products that Intel is putting out on the PC side will be interoperable with the access points that we're providing. So they've been talking about how they're going to open up their IP stack. So in addition to their docking, they'll be doing just traditional Wi-Fi as well. We've been working very closely to ensure that all of the products that we're doing and they're doing are working well together. So obviously to build the ecosystem there. So the two demos that we've got here is first we've got the phone, and we basically made it like a little media hub. This is just a reference design that these guys will be bringing to market. For all intents and purposes, that is a full access point and video distribution. So if you look in the back of that, you can connect to it. Multiple devices can connect to it. You've got USB, and you can add storage in the back of it as well. So you can move pictures and content. So it actually is a full multimedia hub rather than just a video streamer. But we can do video streaming, and then here we just have a speed test, which has got the dial. So when we get to it.
So basically this is
Yeah, so we just hit start here, and we're going upwards of 2.4, 2.7 gigabits per second. It's bouncing around a little bit, but you can see a maintained throughput of over 2 gigabits per second into the phone.
You guys can go closer.
Yeah, far and away, the fastest link that you're going to get into the phone. And then the question is, again, now that you've got this speed, what do you do with it, right? Obviously, it changes the way you can kind of handle your own personal data. You can do full phone syncs, sync and go type of application instantaneously. Point of sale type of applications like kiosks, you can actually buy content and have it, you get off the train station, you go, you buy content, it's on your phone by the time the next train comes. And then the streaming and gaming and low latency applications, that's pretty much what we're driving here. So we're trying to hit all of the different pieces from end to end, from the access point to the client side. And then just where do you Yeah.
Other than raw speed or
Yeah.
raw bandwidth, does AD have any latency reducing features over N or AC or?
No, I think, look, it's basically because of the raw speed. There's,
I mean,
it is optimized for latency because, you know, it was built with, you know, some certain applications that have very low latency requirements. Like it initially was doing some PCI Express, you know, doing wireless PCI Express, wireless USB type of applications. So it does optimize, but, you know, again, once you've got the raw speed, then you can reduce the compression ratios and the latency just goes down.
So it's more than a physical layer change.
Yeah. And here we just, again, we're streaming video. Once again, the Snapdragon 820 platform that it's on has 4K video encoding and capture. So basically you could take pictures, you could take video, and then you can just put it right up on the screen, or take the files, which get pretty large when you're capturing 4K video, and immediately offload them. So once you're part of the 60 gigahertz network, as soon as you have this big files that you're creating, you can immediately offload them onto your home network.
And as we add capacity and complexity to Wi-Fi networks, it's important from a user perspective to provide the intelligence to manage and optimize that complexity. You've heard the buzzword SON, self-organizing networks. In this next clip, we're going to see a great demo of Qualcomm's Wi-Fi SON solution. They've got a Wi-Fi access point and a Wi-Fi range extender with multiple devices connected. So let's take a look to see how this technology dynamically manages the network.
Self-managing is basically when you have a network, you have an access point and an extender or range extender or repeater. How the devices have to be distributed between them so that there is good load balancing going on. A good example would be, if you're in a home, the coverage in your bedroom is not good, but you have a TV there working on Wi-Fi. So how you can improve the coverage is you put a range extender or repeater in the bedroom. So if you carry your phone, the TV works fine with the Wi-Fi there, but in the night you carry your phone over to the bedroom, and then it basically connects to the range extender. That's fine. But in the morning when you come down, on its own, phone may still be connected to the repeater. You're on your first floor now, very close to the access point, but it might still be connected to the range extender, which means the performance on that phone is pretty bad. It'd be better served if it is connected to the access point. So that's a very simplistic example of how, you know, these complications might creep in. So Wi-Fi SON, you know, with its self-configuring and self-managing capabilities, can switch that connection to the right link.
What layer is this done at?
So this is, it is done at the application layer as well as driver. So throughout, I mean,
Good.
you know, so we get the phones actually to do measurements and send back reports. So like, you know, the firmware layer up to like the managing part, the algorithm runs on the user space.
Yeah, so the Wi-Fi SON algorithms are part of a software package that provide along with our chipset. So these are run
So
on
it
our
is on the
processors,
firmware that runs on the
access point.
Why not do it at a lower level?
So-
Like the IP level.
Already know the driver actually know IP in the MAC layer.
Oh, okay.
Yeah, yeah,
Okay.
it's
So
So yeah, I mean, like, you know, we have parts of it in every
Okay.
layer. Yeah. So what we have here is the main access point, which is depicted here on the screen, and we have a range extender outside. We can go there if anyone is interested. And right now, you know, and then both of these access points have two bands. The 5 gigahertz band that is depicted here, and the 2.4 gigahertz band that's depicted up there. And right now we have these 5 devices here that are all associated with the 5 gigahertz band to the main router, since they are very close to the main router. Okay. What we also have is traffic going on. There's a Skype call on this one. We just have a Skype endpoint here. You know. And so the beauty of this algorithm is that while the phones are in traffic for BTM capable devices that supports 802.11k and 802.11b standards, these devices can be moved seamlessly from one AP to the other without like dropping the call or without any impact to the performance. And actually, the AP will make a decision as to what will serve the device best. So when we move these phones closer to the range extender, they will be steered to the range extender. If left on their own, they need the RSSI, the signal strength, to drop really low before they will move on their own. But we don't want, then the call would suffer. And so we don't want that to happen. So, we have certain thresholds and we'll move it over if it will be served better by the range extender. We also do load balancing between the channels. If we see that there is more load on one of the channels, and then we will move devices to the other channel so that the performance is optimal. And so we'll kind of show you.
Yeah. So next, I will move this two phones out to the close to the range extender. You will see they will move it to the extender. Yeah.
So here, the access points work with the phones. Like I mentioned before, they ask the phones to do measurements, and then they will send a request to steer it to the other access point. But the devices can refuse to move. So, most of them, yeah. So we did see, he took two phones. We did see that they moved to the range extender. Next, what I'll do is start traffic on one of these phones. And so as to overload, like I'm going to start traffic on this one, so as to overload the 5 gigahertz band, and we should see phones moved up to 2.4 gigahertz. You will also see that the backhaul link gets shifted there as the traffic starts. Because we have adaptive path selection, and so it selects the best path possible. So the main AP and the repeater are like the link between them is also Wi-Fi. So you don't need to run any cable or Ethernet cable or anything like that.
Now I'd like to move away from Wi-Fi and take a look at two other demonstrations I saw out at Qualcomm. First up, we've all heard about how important millimeter waves are likely to be to an ultimate 5G standard. Now, millimeter wave operates in largely untapped high-band spectrum, and the waves have some challenging propagation characteristics that lots of people are working hard to figure out. In this clip, we're going to see a video link-up between San Diego and New Jersey, where some Qualcomm engineers are going to conduct a live demo of millimeter wave beamforming and steering.
Wave as a part of 5G, the usage of a large number of antennas, beam steering and beam switching as key technologies in millimeter wave. So the testbed that we have running, and Andreas is going to go through the entire testbed, and then we'll be streaming this live from New Jersey. So this is being done in our New Jersey office, and we're on a Skype call from there, and we'll be showcasing how things work. But this is the demo that will be shown live in Barcelona as well, and this is our first live 5G demo that we'll be doing. So, Andreas, why don't you get going?
I love what you've done with the place.
It's very New Jersey.
Yeah. So yeah.
Okay. Are we ready?
Yeah, we're ready also. So this is my colleague in New Jersey. He's gonna actually talk through, most of the demo. What you see here is like 3 different monitors. On the left side, we basically see this 3-dimensional sphere, and then on the right side you see more like the antenna configuration on the mobile side. So you have different antenna elements, and he's going to talk about, once we see it switch and what they kind of mean. This is actually happening in New Jersey. There's an empty floor in the building, so we're using this as our test bed. You can see here is the, this is the base station setup, and here's the mobile setup. And basically we're going to move that around, and then you will see kind of the impact on that. It's a 28 gigahertz link, and in this case it's a point-to-point link. but the base station could support multiple users as well. And it's at 28 gigahertz frequency.
So one of the other things we talked about in the morning was that to validate the technology, I mean, we've got to make sure that it works with different kinds of impairments, including non-line of sight communication, as in it's not just that you can see the device in front of you, but even bending around the corners, etc. And how do you beam steer accordingly?
How sensitive is 28 gigahertz for line of sight compared to 60? Because I'm fairly familiar with 60. Is there a significant difference from the user perspective to 28?
There is a difference over there, obviously, just because of the propagation characteristics. It becomes far more stringent. Non-line of sight is a little more doable with 28 gigahertz, but it's not like there's a huge difference over there. But I think the key part is some of the extensive amount of beam steering that is done in 28 gigahertz. You don't usually see that in products yet, but in 60, but 28 gigahertz, it's something that we believe that it's not only essential, because that's the only way we can bring millimeter wave technology into the mobile world. It's also a place of research for us. How many antennas do we need? We talked about 2 to 4 receive antennas in the morning. But for millimeter wave, that's not yet going to cut it. We need a larger number of antenna elements and so on. So Oscar will go into the details.
On 60 gigahertz also with our 11AD products, right? We demonstrated access using 11AD. And even there we say if you have a closed space, you can still get coverage.
No,
I mean,
I'm familiar with it.
Line of
I'm
sight.
just trying to get how different 28 is to my expectations on 60.
Yeah, and the focus of this demo is not so much on data rates. It's more about, I mean, we already do multi-gigabit per second on the 1180 product. It's really, as Durga and Andrea said, well, beam steering technologies to bring it out into the mobile space.
Gotcha.
Oscar?
Go ahead, Oscar.
So right now, what you're seeing is the base station on the right side of the screen, and the UE on the left side. So both of these actually have a phased array system. So for beam tracking and beam scanning. On the base station we have 128 elements. There are 16 columns, only steerable in the azimuth, so there's no elevation steering. And on the UE we have 4 subarrays of 4 antennas each, and each of those subarrays is a phased array, so they to track the base station. So we'll have a demo of first line of sight operation, and then show how the UE tracks the base station by turning the UE. And then we'll move it back and we'll show how the base station will track the UE in both line of sight and then slightly non-line of sight in one scenario, and then back to line of sight. If you look at the GUI right now, we can see that the base station and the UE are facing each other. So on the right side, where it says millimeter wave base station, the antenna is essentially, the beam is essentially pointing straight to the left of your video screen. So it's just right in the middle because it's facing the UE right now. The UE orientation, essentially the UE is about a 30-degree angle facing out of the screen. So where you see the red patches is where the energy is, and that's, in that orientation of the video, is essentially pointing to that base station. So right now, the base station and UE are pointing at each other, and that's reflected in the beam pattern of the base station and the red heat map of the UE. So right now, we'll first start by rotating the UE, and we'll show that the left part of your screen will track the base station as the UE rotates. And first you'll see that we're on the same subarray. As you just saw that there's a beam pattern change. So we're on the same subarray. These subarrays are located in 4 different spots on the form factor type of antenna module to really show what we would get in a real handset. And as we rotate it enough, that it's a different subarray. So the subarrays combined cover an omni type of space, so they cover the whole sphere. So as we turn the UE, different subarrays kick in, and then each of those subarrays will track the UE, the base station. Now we're moving back, and at some point, there's a column right in the middle of your screen, and that actually creates a non-line of sight type of link. It's It's hard to tell in the video, but that's actually right in between the UE and the base station. And you can see now that the base station is also tracking UE. Before we were pointing almost directly at 0 degrees, and now we're at -20. So as the UE is moving, we're continually tracking it. And the same thing with the UE. The UE is also continually tracking the base station. So now we're again back into a line of sight type of environment. And the UE is now facing the base station, but now the base station is actually at -30 degrees. And this environment actually, even though it's open space like this, it's actually a very rich environment. It's a hard environment to work in because all the windows that you see are very reflective, highly reflective. There's a lot of metal in this environment that are highly reflective. So it's a somewhat tougher environment to form a link and track the link than it is outdoors in many ways. So now we're moving the UE further back. And as we move further back, we'll again position ourselves behind a few columns and then eventually get behind that partition wall. So that wall actually has a stairwell and elevator shaft behind it, which is you can't penetrate because of cinder blocks. And so now we'll start getting into a mode of operation through either reflections from the windows or diffraction along that edge of the drywall. So we're moving back. I think we're still probably line of sight. So at this point, we've probably gone to diffraction because you see that the base station is now -10. So it's kind of shifted back. Now it's pointing towards the edge of that drywall. And the UE is still tracking. And as we move further back, when diffraction is not as strong as reflection, we might see the base station now move, change angle and go for a reflective path. And throughout this, all the turning and moving, going to line of sight and line of sight, we've always maintained the link. There's some variability, but we've maintained the link yet through background scanning of the optimal link. Okay, so now we're in the non-line of sight position and we're still maintaining a link and we're at our highest MCS level, even in this distance. Okay, concludes our demo.
In this final clip, I wanted to show you what's called MulteFire, which is all about running LTE in unlicensed spectrum, which is called LTEU. Now, one flavor of LTEU is LAA, or Licensed Assisted Access. LAA requires an anchor tenant operating LTE in licensed spectrum, which is then boosted with the unlicensed spectrum. With MulteFire, you see LTE in unlicensed spectrum, but without the requirement of an anchor tenant. Let's learn more from Rahul Patel, who's the SVP and GM of Qualcomm's Connectivity Business Unit.
The gist of it is exactly the same in terms of prototype equipment, and it's running in a co-channel deployment, etc. But there are mentioned in the morning as to where MulteFire is useful, why it's beneficial in extremely dense deployments when we have a large number of nodes, and what we can do with it. So this is a graphical representation of what exactly is a dense deployment. You have a large number of users, and you take a look at how much is the C to I, or the interference over thermal. I think that's the one over there, interference over thermal of 40 dB. So this indicates that it's a heavily interference limited system here. So the blue colors over here is where you don't have that many users. Really, it's thermal noise only, but here there's a large amount of interference. It's kind of a way of indicating that. Switch to just disable that, or right click anyway.
Just click inside.
Yeah, so that's
You just take this one out.
yeah, click it out.
Yeah.
All right. Okay. It's exactly the same picture as before. It's a different mall-based environment, and it's a slightly different configuration. But the key point, as Sanjeev mentioned, is there is no licensed spectrum here at all. It's purely unlicensed spectrum at this point. There was a question on what is that P cell and S cell. There is no P cell, there's only one. There's no primary carrier, there's only one carrier here. And we start off by just looking at bidirectional traffic. And as always, we're going to start with every user using Wi-Fi. So in this case, instead of 5, there are 4 sets of nodes. So it's a total of 8 nodes, 4 access points and 4 devices. They're all using Wi-Fi at this point. Similar KPIs again, channel utilization, stepwise, what's the tooth throughput, etc. But at this point, everyone is using Wi-Fi. And the sum rate, just like previously, we saw that before, was about 40 megabits per second. It's exactly the same thing. Now, we are going to, where's the mouse? There it is. I can barely see it. There it is. Okay. So we're going to switch one of the nodes to MulteFire. And that's this one over here. So before we take a look at what happens to that node, let's take a look at the other nodes. All the other nodes, there are 3 more, 3 times 2, 6 of them. They're all using Wi-Fi. And you can see that their throughput is either the same or slightly better than before. So coexistence is still preserved. And on the other hand, the user who switched from Wi-Fi to MulteFire now has a higher data rate. This is both for downlink and uplink. By each of these bar charts, there's like a slightly more solid and a darker region over here. That's the downlink and uplink split. No change in terms of channel utilization characteristics, and it's a fair share of the medium. So what really is the difference, by the way, between this and ELA? And why is it that important that there is no licensed carrier? So in the previous demo when we were doing, it was license assisted. So if I'm a user who's getting served, defer. Okay, now we are good.
Just going to go full screen.
All right. Okay, we're all good. So what's the difference between that and this? So it's only the data that's being transmitted in unlicensed spectrum in the previous demo. But before you do that, there's a scheduling assignment. You're being told to transmit or receive. There's ACNAC and CQI, grants and uplink and downlink. All of those are sent in licensed spectrum. That's why it was license assisted. In this case, there's more. It's not just the data, but all the channels are going through unlicensed spectrum. There's nothing left on licensed spectrum here at all. So in fact, there's a little bit more load in the system. But in spite of that, we still see a pretty healthy gain of MulteFire, even for that single node. Of course, this is for this scenario. But we see a healthy gain for that user who switched while maintaining coexistence. Of course, this was one user who switched out of 4. And now we can do the same thing with the second user also switching to MulteFire. So both these users are now on MulteFire. And they get a fair share of the pie again. Nothing unfair about this part. It turns out that in this case, these 2 users are on Wi-Fi, these 2 users are on MulteFire. These 2 users get, this one was getting 16.5 and now is getting about 16 megabits per second. This user is doing slightly better, and these users are doing slightly better as well. So the overall network capacity, again, which used to be about 40 megabits per second, has gone up to 60 megabits per second. So it is a 50% increase in the overall capacity at this point in time. Of course, this is like a small scenario wherein we have 8 nodes in the same channel. As you densify and add more and more nodes into the network, the relative gains start to creep up.
That's just a sample of the time I spent out in La Jolla. I've got a playlist up on the RCR Wireless News YouTube account that has some really great presentations from Rahul and other high-level Qualcomm guys putting this technology into context for us, so I'd encourage you to take a look at some of those clips. And I mentioned Mobile World Congress at the top of the show. That's February 22nd to 25th in Barcelona, and RCR will be there in force. So I'd encourage you to follow the show at rcrwireless.com, as well as on our RCR TV website and our YouTube channel. In the meantime, I'm Sean Kinney, and thanks for watching HetNet Happenings.
HetNet Happenings is a production of RCR TV. To reach Sean Kinney or to suggest a show topic for HetNet Happenings, you can reach Sean at skinney@rcrwireless.com. On Twitter at Sean Kinney RCR. To find out more about the latest in HetNet and all things wireless, dig into rcrwireless.com.